Okay, now again, I don't know where I laid my chalk. Where could it possibly be? I've got another piece. Okay, again, for the benefit of the video, when you do an integral, you partition the parameter interval, or whatever interval. In the case of a line integral, it would be a parameter interval, and we'll see what that means. You analyze a typical subinterval, write the integral, execute, and then I recommend you check against a reasonable estimate. For a line integral, you have a path, and you have to parameterize the path and partition the parameter interval. And what does that mean? Okay, here's an example. You have a circle of radius 4 about the origin, and you got a wire around the circle. And the wire has a mass density at point xy of 2x plus 3y, meaning that the contribution to the mass of a single interval of distance along the wire is the product of the density times delta S. Okay, so that, for example, if delta S is in centimeters, lambda could be in grams per centimeter. Yeah, the grams per centimeter would be calculated by 2x plus 3y. Yeah. Okay, so you have this circle. Okay, well, what do we have to do? I'm going to go ahead and number these steps. 1, 2, 3, 4, 5, 6. So step 1, parameterize the path. Okay. The path can be parameterized as x equals 4 cosine of t, y equals 4 sine of t, 0 less than or equal to t, less than or equal to 2 pi. Now we should totally understand this, and I believe you do. So there's one way of parameterizing the interval. Now, I could parameterize the interval as 4 cosine of the square root of t, 4 sine of the square root of t, with t going from 0 to 4 pi squared. Or I could use t squared here, so that t would go from 0 to the square root of 2 pi. I could use any parameter in here, as long as I use the same one here and here, with an appropriate interval that includes one complete circle. But this is the simplest, so this is the one I'm going to use right now. Okay? And you've seen much tougher parameterizations when we talked about motion and so forth. So that's not particularly difficult. Okay, so 2, we partition the path. Okay, well, zero equal to t1, less than t2, less than, etc., up to t sub I, and then you got t sub I plus 1, and so forth, up to t sub n, which equals 2 pi. Notice you have this parameter interval. You think of it as an interval along a t-axis, which is totally independent of your xy plane, and you parameterize that interval. You chop it up into small intervals, and then you have your typical sample point, and ti star is in the interval from ti, and actually it should be ti minus 1 to ti. Being careless with my notation, but I think we're all used to that. Okay, so there we have a parameterization of the interval and a sample point in each interval. So 3, we analyze what happens in a given subinterval. Okay, well, in the ith subinterval, x sub I star would be 4 times the cosine of t sub I star. That'd be the x value of your sample point on the circle. Okay, so we could maybe sketch a circle here. And we have whatever the interval on the circle is that corresponds to the interval from ti minus 1 to ti. Looks like ti is going to be somewhere around 2 radians. Okay, the interval somewhere around 2 radians, but it's some interval maybe from 1.97 to 1.973 radians, with ti star being 1.971 radians, whatever. So we have xi star equals this, and yi star equals 4 times the sine of ti star. So here you have your ith interval with sample point xi star, yi star. And you have an interval length. Okay, the interval length I'm going to call delta S sub I, and it's going to equal what? Well, it's going to equal the, how do I want to say this? Going to equal the I don't really want to write it this way, but I'm going to. Okay, because I want to make it as clear as possible. Delta SI is going to be approximately equal to the distance from the point cosine of ti minus 1 sine of ti minus 1 to the point cosine of ti sine of ti. So delta S sub I is going to be approximately equal to, not going to have room to write it there, but I'm going to attempt it right here, to the, yeah, I'm not going to have room, but we'll try anyway. Well, to the x displacement squared, which is the cosine of ti minus cosine of ti minus 1 quantity squared. I'm going to have to extend this square root sign. It almost looks like a k, but that's a parenthesis cosine. Plus the sine of ti minus the sine of ti minus 1 quantity squared. Now, the cosine of ti minus the cosine of ti minus 1 is going to be approximately equal to the derivative of the cosine multiplied by delta t. So this is approximately the cosine of ti. I'm running into a notation glitch here, and again, that's not unusual. So I'm just going to write what it is. It's the negative sine of ti star delta ti being ti minus 1, the width of the interval. And why this? Well, this is the derivative of the cosine. Now, just by a tangent approximation or a differential or whatever, derivative of cosine is the negative of the sine, which is the rate with respect to t at which the cosine is changing. So if we multiply the rate at which the cosine is changing, which is going to be approximately the negative sine, the derivative evaluated at your sample point, by the change in your parameter ti, you get the change in the x-coordinate of this point. And that's part of your Pythagorean theorem, okay? So, and then you do the same thing with the sine. And the derivative of the sine is the cosine. So you have this. So this is equal to the square root of the sine squared of ti star plus the cosine squared of ti star multiplied by delta ti. Because I can factor out the delta ti squared under the square root. Outside the square root, it'll become a delta ti. So it's this. Now this generalizes, but the lesson is that, okay, then total distance around the arc, which we already know because it's just pi times the diameter, okay, 8 pi. And you know what? I was really pretty careless here because your parameter is 4 cosine of t and 4 cosine of ti, so I'm going to have to put a 4 out here, multiplies through everything, and multiple 4 here, and we're going to have a factor of 4 in each of these. I don't have room to write the 4 times here. I'm going to put 4 times here. It's not a 4th root. I can sneak in a 4 here. Okay, then the integral is going to be 4 times the integral of this. Of course, this is just 1, and the integral goes from t equals 0 to 2 pi. This is just 1. Integrated dt gives you t from 0 to 2 pi, gives you 2 pi, multiplied by 4, you get 8. So there's your circumference again. Now that's not what we're trying to find. What we want to do now is ask ourselves, okay, this is great. Right there is your typical arc distance. But what is your mass of the interval? Okay? Well, that's really easy. Once you have the whole thing parameterized, okay, I'm just checking my numbers. Okay, so now delta SI is 4 times the square root of cosine squared, sine squared at ti plus the cosine squared evaluated at ti times delta t sub I. What's the mass? Well, the mass of any interval of length delta s is going to be the average density times the length. So I'm going to say lambda average times delta si, but the average value of lambda is going to be approximately lambda at ti multiplied then by delta si to give you your mass increment. And now we don't really need all the rest of this. So we're going to say lambda of t sub I, remember that rho and that should be ti star. Rho evaluated at x, but what's x? X is your function evaluated at ti star. We have this, and it's not rho, it's lambda. And lambda is 2x plus 3y, if you recall. So that's 2x of ti star plus 3y of ti star delta si, and x of ti star is 2 times the cosine of ti star plus 3 times the sine of ti star delta si. Well, the sum of the delta mi, well, that's your mass, sum from I equals 1 to n of your delta mi. That's the sum from I equals 1 to n of this expression, so let's do it again. 2 cosine of ti star plus, that's, 3 sine of ti star delta si. And this approaches through the miracle that occurs that, again, you're doing really well in the course, so I recommend that you understand from your first year calculus how this integral, how this sum approaches the integral from 0 to 2 pi, 0 to 2 pi because you partitioned the interval from 0 to 2 pi. So as I goes from 1 to n, your intervals go from right next to 0 to right next to 2 pi. So you're summing up all these contributions from all of the intervals, and you get 2 cosine of t plus 3 sine of t times the delta si, which is 4 times the square root of cosine squared of t plus the sine squared of t dt. Now this is actually a very easy integral because this thing comes out to be just 1. Now this is a lot like an arc length integral. So okay, you can compare that to what you've done for arc length. Okay, well that's stage 3. You've analyzed what happens on the typical subinterval. Then for execute, and then 5 compare it with a reasonable estimate. Now, what I've done here, I've given you a density function. It's actually got some symmetry to it. It's negative as much as it's positive, so you're going to get 0 if you do this integral. If you integrate, you're basically just integrating a cosine and a sine, each from 0 to 2 pi, and any of those integrals is 0. So this isn't a very realistic density function. (2x plus 3y) in the first quadrant is equal and opposite to 2x plus 3y in the third quadrant. And the same holds for the second and fourth quadrants. So since everything is symmetric with respect to the origin, it follows fairly immediately that reasonable estimate is that this thing is massless. Of course, there's no such thing as negative mass, but that shouldn't stop us. This is mathematics, not physics. So if I'd have given you a different function where the cosines were squared and the sines were squared, then everything would have been positive here, and you would have gotten a non-zero integral, and you would have gotten a positive integral. It doesn't matter what the density function is, it basically gets plugged in to your arc length integral. But you want to get in the habit of analyzing the thing locally, analyzing a typical subinterval. So any line integral you do is going to be done by completely analogous steps. Okay, now there are ways to shortcut it, there are ways to go to formulas and use formulas. And you can read in your book what the formulas are, but you see from this example, if you understand it, exactly what the formulas are telling you. So you don't really need the formulas, but yeah, I mean, I did really well in this course when I took it. First math course I did really well in, actually. And maybe the last, I don't think so. But I don't think I ever did as well in a math course as I did in this one. Okay, and it was at a very high level school of technology, and I really aced the course about as well as could be aced. Although there were a lot of smarter people, I probably worked hard. And my point is, I relied on those formulas, but I always thought about what they meant. Okay, and I was good at remembering formulas, but I always went deeper to what the formulas meant, how they were derived, so that I always felt very secure when I was doing a problem. So I do recommend that approach. Rely on the formulas as much as you need to, but try to understand as deeply as you can what's going on. Okay, well, that's the first thing. And that's all I'm going to say about line integrals, because you're going to have your web assigned and so forth. And you'll see how it all works together if you understand this one example. The paths might be more complicated, but as long as you can parameterize them, you can do all this. Okay, now that's it. Next thing I want to talk about is conservative fields. And I'm not even going to talk about what vector fields are. It'll be kind of obvious from the context, and it's not a section or a topic that people have a tremendous amount of trouble with. So, given our constraints of time and so forth, and the way you're doing in the course, I'm going to leave that to you. Once you've worked through it, you'll have a better perspective on some of this stuff. But I think you're going to understand what I do anyhow. Okay, let's let f of xy equal x squared y cubed plus 3y. Then the gradient of f, very easy to calculate, so I probably screwed up, but it's 2xy cubed I plus 3x squared y squared quantity plus 3j. Okay, so there it is. And okay, now I'm going to cut to the chase here. The gradient of f is a conservative vector field for any differentiable, and I could use more words to describe the differentiability, but it's got to be once differentiable in x and in y and all that stuff. For any differentiable function f. Okay? Now, I haven't even talked about what a vector field is, but there's a conservative vector field, and they're of great interest. You've had physics, you've done well in physics, you understand the importance of conservative functions, okay, like gravitation function, the electromagnetic field. These are all conservative, okay, elastic material, and let's think of a spring. These all give you conservative force fields, or conservative, well, they're conservative in many ways, okay? And then your function f is called the potential function. For the field del f. A conservative field has the important property, and I'd love to derive this, I always do, but I'm not going to be able to here, in the time we have under our constraints. The integral and I've written this as a closed path, and right now I don't want to do a closed path. The integral over C, where C is a path of del f ds equals f of b minus f of a. This looks a lot like what you do with an antiderivative. And in fact, the function f acts like an antiderivative of the function del f. Now let's be a little clear about what I mean by C and what I mean by A and B. Okay? Where C is a path, where the integral is a line integral, and there are conditions on this, like the line integral has to pass through a region where del F is continuous, differentiable, etc. Okay, or at least continuous, and yeah, continuously differentiable. You can work the conditions here, and they make perfect sense if you understand the concepts. Okay, so the integral is a line integral, and A and B are the endpoints of your curve C, of your path C. Okay, you say curve, we use C because it stands for curve, and your path is typically a curve, but it could be a bunch of straight line segments, and you'll see integrals of that nature. Okay, so that's the fundamental theorem for path integrals. It's just like the fundamental theorem of calculus, where A and B would be the endpoints of an interval of a single, endpoints of an interval on a given axis. This takes us into two-dimensional space in the examples we've looked at, but it also applies in any dimension, and it extends from 2 dimensions to any dimension just by adding, a z and derivatives with respect to z, and then if you want 4 dimensions, you can have another dimension, which you could represent by the variable w and so forth. And if you got a whole bunch of dimensions, you call them like x1, x2, x3, dot, 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 xn. The expressions just extend, just like they do in linear algebra, and you're familiar with how that works. Okay, so here we have this fundamental theorem, okay? And that's a big deal, really big deal. Okay, it's a fundamental theorem, and to put it in the context of physics, if you move through a conservative field, you have a potential function. It's like your potential energy function, okay? And if you move from one point to another in a potential field, in a field that's governed by a potential, the field being the gradient of the potential, then the work you do from one point to the other is dependent just on the endpoints, and it's the potential at this point minus the potential at this point. So in a gravitational field, I lift from here to here. I have a certain potential energy here and a potential energy here. The work I do depends just on the potential energies. Okay. At the 2 endpoints. Again, something you're familiar with from physics.